Hi, I'm Casey. Welcome to the Centre for Design of Quantum Materials. So I'm going to walk you through our lab today. What we do in here is we grow some materials and we analyze them, and we will do all of this in what we call in a vacuum environment. So that's where there's no air, no water, kind of like being in space. The possible applications of these materials are so vast, it's hard to just pick one, but one of the really exciting things, I guess, is flexible electronics and lots of new superconductors that hopefully work at slightly higher temperatures. So what I'm going to show you first is our growth system here. So we use a technique called molecular beam epitaxy. This sounds really complicated, but it's not so bad. So what we have at the bottom here is we have our cells. So in there we have our materials. Usually they're metal, so like tin, nickel, niobium. And we heat them up to a really high temperature so they go from a solid straight to a gas. And then in front of these, we have these shutters up here. So we can control when we open and close them. And basically, when we open them, it just kind of all comes out like a spray paint onto our substrate, which is held at the top here. With this technique, we're able to get very, very good control over our growth. So we can grow down to single layers. We can grow lots of different materials because we have lots and lots of cells. And everything we grow is very, very clean because it's in this vacuum environment. So that means there's no dirt on there, there's no dust, there's no water. So it's very, very high quality. We actually have two machines here. So this one we use to grow metal oxides. So we have a big ozone machine over here that produces oxygen and ozone for us. And in this direction, which I'll show you in a minute, we have our GM2 setup. Currently it's being baked, which means that we're trying to clean it out from being exposed to the air, and we'll show you that soon. So I've shown you GM1, and this is what we call GM2. So GM2 I actually know a little bit more about because that's the system I work on. So we use this to grow 2D materials. It's really hard to understand what a 2D material is when you live in a 3D world. So how to think of it is, if you have a big cardboard box, a 2D material is basically a sheet of paper. Compared to that cardboard box, it has zero height. Right now, you're lucky because we're actually baking it, so this doesn't happen very often because it's quite an intensive thing to do, I guess. These are all at vacuum, as I said, so to fix it, we have to bring it back to air, and then that means that once we're fixing it, it gets a little bit dirty, water gets in there, dust. So we try as much as we can to stop that happening whilst we're doing it, but after we also need to bake it. So that's what this lovely blue tent is here. What we're doing is we're basically heating everything up to a high temperature so that all the water and the dust comes off and it leaves the system back in a vacuum state. With everything being in vacuum, it's not very easy to move things across. So we have quite a big setup here. We have to get things from one side all the way to the other. So that means we have to make use of these dials to move our trolley across. And as you saw over there, we actually have a carriage because we have to change height. So it means that we're having to load samples into it to move it down, to move it to another height, to go into another system. And we're going to show you a transfer in that system now.
Hi, I'm Geza. I'm working on the spectroscopy part of this group. And now that we have our materials, we want to look inside of them. In fact, we want to look at the smallest particles of our sample, which are the electrons. So before we can do that, we have to transfer the sample all the way from the MBE system into our spectroscopy system. So because we are all in vacuum, we never have to get them out of the system and can transport them directly. Now our sample is on our manipulator and we can actually move it around. We even have a little door that we can close it first so we don't lose the sample in our system. And once the sample is in our system, we drive it all the way down into our measurement chamber to measure our electronic structure. So now that we have the sample in the system, how do we make those invisible particles visible? For this we use light. And it was actually no one else than Einstein himself who more than 100 years ago explained the effect. So what this means is if we shine light on our sample, we will kick out the electrons inside the sample and we can detect them. These electrons are directly related to what they do within the solid. We don't use any light. We actually use very intense light to actually have enough energy to kick the electrons out of our samples. For this we have either a laser source or a helium lamp. So our sample is currently went from the upper chamber here in our measuring chamber. And if we now shine the light on it, we can detect it with our analyzer. The angle resolved setup does not just allow us to get one shot and one energy, we actually get a whole picture of what's going on in our solid. We get the so-called band structure. It's like a roadmap of a material, and every material has slightly different roads. Electrons really like to stick to these roads, and it's very hard to jump from one road to another. But we don't just study these roads of the material, we also try to manipulate them. By applying strain or by growing different materials, we push the roads so close together that the electrons can now jump from one to another. We can look at very different effects with this, for example, at magnetism or superconductivity. A superconductor conducts without any loss. The downside of this is this only works at very, very low temperatures, and it wouldn't even work on the coldest place on Earth. So this is why we also use helium. With this helium canister, we can cool our whole system to temperatures down lower than minus 260 degrees Celsius. This is necessary so we can actually study and understand all these effects, so that at some point we can tune them and actually use them in our modern technology.